kilometers in virtually every direction. Use the same Mars tape is out here. I still believe those sediments have to be down there someplace. Those lake-like sediments must exist, but they have been covered over by lava by the time we got there. And so we had no access to them, and we've never seen them. Unfortunately, off the distance, 2.5 kilometers southeast of our landing site, there is this marvelous range of very ancient hills. They're older than the rocks on the plains. They're sticking up through them like islands in the sea of basalt. And so we sprinted rover speed to get to the Columbia Hills, hoping to get there and do a little science before the rover died. The vehicle was designed to last for 90 Martian days. It was designed to travel 600 meters over its lifetime. We reached the base of the tallest hill in the range. We named it Husband Hill. The Columbia Hills were named after the Columbia Space Shuttle. Rick Husband was the commander of Columbia when it went down. And over a period of hundreds of Martian days, we did the first ever mountaineering on another planet, climbing to the summit of a hill called Statue of Liberty. And I wish I had the ability to take you through this diversity of different kinds of rocks that we found on our way up and down Husband Hill. There's an incredible diversity, very, very complex geology. I'm going to just show you two of my favorites, but there are a bunch more. So I'm going to show you first some of the rocks that we found on the northern face of Husband Hill as we worked our way up towards the summit. This is a rock called Methuselah. This is a mosaic acquired with our microscopic images, multiple images. That whole scene that you see there is about 10 centimeters across. This is a finely layered rock. Elements of its texture tell us or suggest to us that what we're seeing is a high-energy explosive deposit, probably rather than being explosive volcanic, it's probably impact ejecta, stuff that was thrown out of an impact crater. In this particular area, the ridge that I showed you, all the rocks have essentially the same elemental chemistry. It's a complicated plot, but what it shows you on this axis are some of the major elements that are detected by our X-ray spectrometer. And what I've done here is simply ratio the concentration of that element to all that lava that we saw in element planes on an element-by-element basis. Notice this is a log scale. Okay? So these are a bunch of different rocks, all from this ridge. And in terms of their elemental chemistry, they're all the same. They're all made of the same stuff in terms of which chemical elements are present. Okay, there's some interesting patterns. It's, chromium, phosphorus, the same things. But the important point is all the rocks in this region of outcrops have the same elemental chemistry. But when you look at the minerals that are present, the way in which those atoms are arranged to form the chemical compounds that are present, they're completely different. Okay, these are 4 different rocks. These rocks are literally within a scale the size of this auditorium. Some of these outcrops are 5 meters apart, 10 meters apart. Some of them are vertically half a meter apart. Some of these rocks you see essentially an unaltered basalt. You see olivine, you see pyroxene. It hasn't been weathered, it hasn't been changed much. Okay, if you look at the iron oxidation state, Fe3 plus Fe total, 0.4 really isn't oxidized a whole lot. And then literally a few meters away, right next door, you will see rocks that have no olivine, no pyroxene, heavily altered, lots of fine grain called nanophase iron oxide. There are minerals in here like hematite, which is an iron oxide. Goethite, yellow stuff. In the spectrum here in yellow, iron oxide, or hematite is an iron oxyhydroxide. Water is required for its formation. Okay, and it's found in immediate proximity to these relatively unaltered basaltic rocks. So, what we infer from this is that there has been an alteration process that has taken place here. It's been effectively isochemical. It has not changed the chemistry, it has just changed the way in which the atoms are arranged with one another to make different minerals. And so that speaks, given the fact that you see minerals like hematite, and especially hematite, water certainly has to have been involved. But it was at a very low water-to-rock ratio. You didn't have great gushes of water flowing through this stuff, dissolving away different chemical elements and leaving others behind. Instead, what you had was an effectively isochemical process, very low water-rock ratio, and highly localized. So think steam vents, small amounts of vapor coming through the rocks and locally changing the mineralogy while leaving the chemistry the same, and in some cases, not even touching rocks that might be a few meters away. So this is a local alteration process that speaks of water that are low water-to-rock ratio. A lot of other interesting rocks on the hill that I'm not going to try to tell you about. We went over the summit of the hill, came down to the south, and we spent an enormous amount of time in the vicinity of this thing here we call home plate. Home plate is a plateau of layered volcanic rocks. These are explosive volcanic rocks. Here's a close-up image from orbit. This shows you home plate. It's about 80 or 90 meters in diameter. It's a couple of meters tall. And this shows the path that the rover followed as we were exploring along the vicinity of home plate in the place that we came to call Silica Valley. You can sort of tell, just looking from the back, that we did this spaghetti here, that this was an interesting place. Now, Spirit had a tough time. Climbing a mountain was not something this rover was ever designed for. We really beat on this vehicle, and after about 800 days of this, the right front wheel failed. And so now, this wonderful rover that used to be able to do 100 meters in a Martian day, a good day is 5 meters, dragging this dead wheel through the soil. We had to drive the axis and drag the wheel along. But the silver lining to all of this was that we dug this marvelous hundreds of meters long trench through the Martian soil. And at the end of one of these drives, this place we came to call Silica Valley, we saw these bright white deposits in that trench. That attracted our attention. We went over and we made a measurement with our alpha particle X-ray spectrometer. That's the silica line. This stuff is 91% pure SiO2. 91% pure SiO2. Also rather highly rich in titanium, which I'll get to. So very, very high concentration of silica. Now we first found them in the soil. We then immediately thought, oh wow, this is interesting. I wonder if there are any very silica-rich rocks nearby. So we found some rock outcrops, we made some measurements. This is a mosaic taken with our images, 6 centimeters across. Made measurements with our alpha particle X-ray spectrometer. Again, very, very high silica. This has a point. Looked at it with our infrared spectrometer. Shows clear signature of silica being present, and it is hydrated amorphous silica. This is not quartz, this is not beach sand, this is opal. Okay, so that's what we're seeing here. Now, I've compared the spectrum that we actually observed in purple with a couple of silica deposits on Earth, one of which is a rock that is rich in silica through and through, and another is one that just has a silica coating. And so at this point, we had a lot of debate on the team. Well, are the rocks just coated in silica, or are they really, really rich in silica through and through? And of course, this is the kind of problem that our rock abrasion tool is designed to answer, but we wore the rock abrasion tool out back on some of those other rocks up on the hill. So we had to find another way of getting into the rock. What we chose to do, we found an outcrop where there was some topography, and we just drove over it with the wheel. One force trauma in the service of science. And the rock that we were aiming for didn't break. But there was one that we were not aiming for right next to it that did break. Maybe an innocent bystander. And not only did innocent bystander break off, but it obligingly flipped itself upside down, exposing a fresh surface. And we measured the composition, and it was more than 80% silica. So these rocks are rich in silica. So we have two different hypotheses for what may have happened here. One is that what we're seeing is what's called a siliceous sinter. This is stuff that you find in deposits associated with hot springs. So when water with a kind of neutral pH is at high temperature below the surface of the body, silica is a pretty soluble species. It can pick up silica in solution, comes to the surface, it's hot, so it's boiling, it rises, it gets to the surface, it cools off, and that silica gets precipitated out. And you can make very high concentrations of silica that way. And these are some silicious sinter deposits from hot springs on Earth, and they're very, very nice matches for data. But here's another possibility. I kind of like this one. This is some work that was done by Dick Morris, a member of our team. And what Dick did was he went to Hawaii, where there are volcanic fumaroles. And the vapors that are coming out of these fumaroles are extremely acidic, very low pH, pH of 1, pH even less than that. And it turns out that the solubility of silica in water is highly pH dependent. And at very low pH, in acid, silica becomes one of the least soluble species. So here's a rock. This is a piece of basalt that was sticking into the flow of vapor from the fumarole. So Dick takes this rock and he slices it up like a loaf of bread, and then measures, just look at the left-hand side here, the elemental chemistry as a function of depth within the rock. So the stuff near the surface, that's the stuff that was subjected to these highly caustic vapors. And then now, down in here, you just have chemistry of typical basalt. But these are the concentrations of different chemical elements a liquid silica does. Way up. In fact, this has got to be just pure chance. The right at the surface, the concentration is 91% silica. And look at the other elements that is enriched. It's titanium. Everything else gets leached away. Those are the two insoluble species at that pH. So what this may be is the signature of essentially volcanic fumarole. Again, hot, caustic vapors coming up through the rock. That's all I have to say about spherics. Let me give you a little bit of atmospheric science. We've got instruments that can pick up. We have the capability to monitor the amount of dust in the Martian atmosphere by looking directly at the sun and seeing how much the sunlight is attenuated by dust in the atmosphere. We have these wonderful profiles of dust concentration in the atmosphere as a function of time over multiple Martian years now. You can see little local dust storms and all sorts of factors. Wonderful record of the climate. Our infrared spectrometer can look up, and by looking at the width of the 15-micron CO2 band, we can actually construct vertical temperature profiles within the atmosphere. So here are a bunch of profiles through the atmosphere, different times of day. You get inversion layers, all sorts of wonderful boundary layer physics that goes on. You can even do high time domain measurements, where these are measurements, very short duration measurements over a period of minutes, and you can actually see this is convection. The temperature scale, the colors denote temperatures. And you can actually see blobs of hot, warm vapor rising off the Martian surface, so you can see convection in the atmosphere. A really cool thing that we did with this instrument is related to an instrument that was on the Mars Global Surveyor orbiter. Basically the same instrument. They can both do atmospheric sounding, one looking up from the Martian surface and one looking down from orbit. We actually did an observation where we commanded the one in orbit to look at the instrument on the ground, and the one on the ground to look at the instrument in orbit. So you're basically looking at a single column of atmospheric gas on Mars from both ends. The solid lines here are the data from orbit. The solid points here are the data from the ground. No fudging. We didn't cheat. And look how well they meet. So that was pretty cool. Right now, I know there's a bunch of astronomers in the audience, so this is the astronomy portion of the talk. Don't blink. It's going to go by really fast. Mars has two moons, Phobos and Deimos. There was a period of time in which Spirit had so much power that we would turn the cameras on at night and look up. So here's pictures of Deimos. Here's a picture of Phobos. This is Phobos, as observed from the summit of Husband Hill. You can even see Stickney Crater. Here's a picture from the spacecraft. You can see a little crater on the moon. Check this out. A solar eclipse. Phobos passing in front of the sun. There's no science in this at all. We just did it because we could. Here's a lunar eclipse. So watch this one. This is Phobos passing into
night, and we look up and there's this streak across the sky. We first thought maybe it was a spacecraft. Well, no. I mean, they're old, derelict, the Viking orbiters, they're still up there. Either one of those. But it turns out that you can predict when meteor showers should occur on Mars, and this occurred during a predicted meteor shower, and the orientation on the sky matched the radiant of that shower they happened to bring. So we're pretty confident that was a meteor. And then for all you extragalactic astronomers, there is the Large Magellanic Cloud as imaged from the summit of Lisbon. And that's the end of the astronomy case. But I thought that was kind of a nice picture. All right, let's go to opportunity. The landing site for opportunity was not chosen because of its topography. No big impact crater, no channel flowing into it. We chose it instead based on the mineralogy. So on the right, what you have is data that were acquired from orbit with an infrared spectrometer. Blue is lava, but the red and green and yellow, that's hematite. Okay, again, hematite's an iron oxide. It's a mineral that frequently forms as a consequence of the action of liquid water. So this is like a chemical beacon visible from space saying, hey, come land here. Water may have been here. We landed at Opportunity. It's a very nice, topographically smooth, flat landing site. You can see this is the trajectory that we drove for the first part of the mission. That's a 2-kilometer scale bar there. Again, the thing was designed to drive 600 meters. We landed in a tiny little crater called Eagle Crater. Spent about 60 days there. Drove to Endurance Crater. We spent 200 days there. And then a long 6-kilometer drive to finally get down to Victoria Crater. I'll show you all those. Here's Eagle and Endurance. Eagle Crater, size of this room, maybe a little smaller, tiny little thing, wheel tracks everywhere. We kind of work this place over. Endurance Crater, about 150 meters in diameter, maybe 20 or so meters deep. We went down into it. We did a stratigraphic section, the first stratigraphic section of the on another planet. The rocks here are extraordinary. The rocks here are incredibly rich in sulfate salts. Roughly 40% sulfates. They're a finely laminated sandstone, sand-sized grains of sulfate-rich material, finely layered, finely laminated, and then shot through with these little round things embedded in the outcrop like blueberries in a muffin. Okay, and the muffin is soft, and the blueberries are hard, and the muffin erodes away, and the blueberries fall out. And it turns out the blueberries are where the hematite resides. So it's a bizarre phenomenon. This is a complicated plot, but it just makes a simple point. The yellow is SO3 as measured by our alpha particle X-ray spectrometer. And this stuff is roughly 40% sulfates. When you try to calculate the mineralogy from the elemental chemistry, you infer about 20% magnesium sulfate, about roughly 10% calcium sulfate, and a roughly 10% an iron sulfate called jarosite. And then there's a bunch of other stuff as well. So that's inferred from the elemental chemistry. You can also do it from the infrared spectrometer, and this is looking into an Endurance Crater from their infrared spectrometer. All the red stuff is where the bedrock is exposed, and that's the sulfate. And when you match the spectra of known sulfates in the infrared, you get the same numbers. 20% magnesium sulfate, 10% calcium sulfate, 10% jarosite, the iron sulfate. Now, the Mossbauer spectrometer is only capable of detecting iron-bearing species, but it should be able to see the jarosite, and sure enough it does. Here's a very nice Mossbauer spectrum. You can see some hematite, that's the blue peaks out here, but these big yellow peaks, responsible for this peak of the spectrum, that's jarosite. You can see the chemical formula for jarosite here, lots of OH. You need water to make this stuff. But the interesting thing about jarosite is a very environmentally informative mineral because it only forms at very low pH. It is not even stable above a pH of 5. And on Earth, it typically forms at a pH of 3 or 2 or 1.
So people see data like this and they run around saying water on Mars, water on Mars, okay, fine, but it was really sulfuric acid on Mars. Very acidic environment. Now, we were very interested by the blueberries. The blueberries are 4, 5, 6 millimeters in size, and the field of view of our Moss power spectrometer is about 1.5 centimeters to 2 centimeters. And so if you try to isolate a single blueberry to measure its composition, your field of view winds up having a little bit of blueberry and a lot of muffin in it. And it's hard to make a measurement. So what we needed was a gathering of blueberries. And we found one. This is a place where there was a little bowl-shaped depression that the blueberries had rolled down into. We called it the berry bowl. And we stuck our Moss power spectrometer inside it, and the light blue spectrum, that's the spectrum of berry bowl. And extraordinarily strong phenotype. After doing lots of work on these, we've concluded that the blueberries are made at least 75% hematite. Now what we concluded is that the hematite blueberries are concretions. Concretions form typically in sedimentary rocks on Earth. They're saturated with liquid water. There's some mineral, hematite can be such a mineral, that's dissolved in this stuff and it wants to precipitate out. It finds a little nucleation point and it grows. And it grows and it grows and it adds layer upon layer, making a little hard spherical nodules, sort of like pearl. Now, one of the characteristics, if you think about where the concretions grow, each growing concretion draws from a body of fluid around it. So it sort of forms an exclusion zone. The water from that body of fluid goes into that concretion. And if another concretion wants to grow, it's got to grow at some distance away from it, otherwise it's going to be starved of the minerals it needs. And so what happens is that if you look carefully at the distribution of concretions in a rock, they don't tend to be random. They tend to be more uniform than random because each concretion carves out a little volume for itself. It's sort of like the distribution of trees in a forest is not random because each one has a canopy in their shade and trees can't grow under. And in fact, when you do nearest neighbor statistics on the volume distribution of the blueberries, you find that it is markedly more uniform than random. Again, consistent with the concretions. We also found some very interesting sedimentary structures in these rocks. Now, most of the stratification that we see in these rocks is consistent with the thing that transported the sand grains having been wind. We see lots and lots of evidence of basically preserved ancient sand dunes. But in a few special places, we also see evidence for liquid water. This comes in the form of these little concave upward structures, cross stratification, that is on a scale that points to it being liquid water. This is some work done by Dave Rubin and the Geological Survey. This is flume experiments with sand being transported by water, 40 centimeters across there, and you see what you get are these ripples that have very sinuous crests. And you have sinuosity in the crest over characteristic length scales of 5 to 10 centimeters. Now here it is simulated in a computer. Sinuous crest ripples propagating downstream, and what is left behind is this trough geometry cross stratification, these little concave up smiley shapes on a scale of typically 5 centimeters or so. And it is that physical length scale that points to water as being the fluid that's in the transport. Again, work from Dave Rubin. This is some of this cross stratification from these little water ripples. This is from some sediments from the Colorado River on Earth. And here it is on Mars. Little concave upward smiley shapes in the rock, 5 to 10 centimeters in size. Here's a really good one. This is a rock called Hornbill. Just shot through with these little things. Here is a piece of hornbill showing these little concave upward cross stratification. And at the exact same scale, this is some sedimentary rocks from the Archean on Earth that shows the same kind of structure. This is rare. Most of the rocks don't look like this. But what it says is that some of the water that was beneath the ground that helped precipitate out these accretions occasionally came to the surface and flowed across the surface, making this cross stratification in the rocks.
You'll notice that all of the different craters here are named after famous ships of exploration. So Eagle was the Apollo 11 lunar lander endurance ship. Victoria was one of Magellan's ships. Magellan left Spain with a flotilla of 5 ships, 260 men. Spent 3 years at sea. Magellan himself was killed in the Philippines. After 3 years out, the one surviving ship, which was the Victoria, with 18 surviving sailors from the original 260, limped back to Spain. So we chose that name for this crater thinking it would be an apt analogy with our poor little beat-up rover driven by 18 surviving graduate students if we ever made it. But I'm pleased and proud to say that we did. In a wonderful coincidence, at virtually the exact moment that we pulled up to the rim of the Endeavour crater after this long 6-kilometer drive, of Victoria crater, the Mars Reconnaissance Orbiter got to Mars, turned on its high-rise camera, and took this marvelous high-resolution color image of Victoria crater. I'll blow up just this little portion. There it is. If you look carefully, there's opportunity. And if you look really carefully, you can even see the shadow of the camera mask being cast on the Martian surface. It was really nice to see our rover again. We spent 2 years exploring Victoria crater. We drove along the rim. We went down inside the crater. I don't have time to tell you about any of it, but it was really cool. Now, after 2 years exploring Victoria crater, we had to decide what to do next. By this point, we've been on Mars for 5 years with a rover that was designed to last for 90 days. What the hell? It's all gravy at this point. We've got to go for it. Okay? So what we decided to do was to strike out for Endeavour crater. Okay, so here's the Endurance crater, a little dot up here. There's great big Victoria crater, 800 meters in diameter, where we spent 2 years. And we set out to the rim of Endeavour crater. Endeavour's about 22 kilometers in diameter. It's hundreds of meters deep. What distinguishes Endeavour is that unlike these other craters are formed within. They excavate into the very same sulfate-rich sandstones that we drove around on for many years. Endeavour, on the other hand, is a much older crater. And the rim of that crater is sticking up through that sea of sandstones, very much like the Columbia Hills sticking up through the basalts. And they provide access to a very, very different geological material. So what we truly believed was that if we could get to Endeavour, it would be like the mission starting all over again. It would be brand new geology. And indeed it was. It took us 3 years of driving across the plains, 80 meters a day, 80 meters a day. 3 years of that. We had 34 kilometers on the odometer by the time we finally reached the rim of the Endeavour crater. But we got there. This is a portion of the rim of Endeavour. So this is a ridge. We named it Shoemaker Ridge after the late Gene Shoemaker. That is sticking up through these sediments. So now we're seeing the actual rim of this ancient impact crater. And just as everything changed when we crossed the boundary between the plains at Gusev Crater and the Columbia Hills, as soon as we crossed the boundary here between these sulfate-rich sediments and onto Shoemaker Ridge, again, everything changed. Most of the rocks that we have found on Shoemaker Ridge look like this. This is a rock we named Chester Lake. It is for the most part fine grained, but is shot through with great, big, angular chunks of stuff. We tend to show kind of a further line. You can actually see a texture to these things, which is, turns out is radial through the center of the crater. That's a clue. These rocks are all over the place. They all have basically the same elemental chemistry. This is a bunch of different rocks from up and down Shoemaker Ridge. Same kind of plot that I showed you before. They're all made of the same composition. It's basically a basalt. What this rock looks like, its texture, its tendency for these angular chunks to be aligned, it's a very good match to what's called a swayite breccia. This is a form of impact ejecta
It's found in impact craters, particularly on Earth, also on the Moon, within a certain size range. And it is ejecta that are deposited during the final stages of an impact event. And basically, you have a wind, sort of vaporized rock that is flowing outward from the impact point, and it is entrained in it. A lot of fine-grained stuff, but it's also a powerful enough wind that it can blow chunks the size of your fist through the air, and then it settles out. And this is what this stuff looks like. So here we seem to be seeing a particular kind of impact ejecta that is common on Earth. I'll get back to it. There was another kind of rock that we found, and it was represented by a rock that we named Tisdale and several others around it. And here's the interesting thing about this one. This is a little crater that we named Odyssey. It's about 20 meters in diameter, so it's excavated through the surface rock and down to a depth of, oh, I don't know, maybe 4 or 5 meters. And it threw out chunks of stuff. Tisdale, here's another one. This one's called Kid Creek. These are those chunks. This is a breccia also, but it's a very different kind. This is what you would call lithic breccia. This is a chunk the size of your head. Okay, big, big chunks of rock, all glued together. Here's Tisdale. Okay, this is a lithic breccia. It looks very much like breccias that one finds on the Moon. The elemental chemistry of this one is similar, though a little bit different, from the other rocks, the swayback breccia that I showed you. Very similar to some of the rocks that we see in the Columbia Hills, with one big exception. There's one thing that distinguishes this rock from every other rock that we've seen on Mars geochemically, and that is it's got a lot of zinc. It's got a huge amount of zinc in it. Now, why would there be so much zinc? Okay, on Earth, we find zinc particularly in high concentrations in things that are called volcanic massive sulfide deposits. And these are associated with rocks that have been hydrothermally altered. Hot water coursing through the rocks, moving things around, and zinc is an element that is particularly easily mobilized by this hydrothermal flow. And when you go to places like zinc mines on Earth, for example, these are found in Canada, these are places where the zinc has been mobilized by hydrothermal flow. The feedstock from mines that we find, these are commercially viable mines, typically have like 1 to 5 or 8% zinc in it. Here's a rock on Mars that's half a 8%. It's almost a zinc ore. Okay? So what we think happened here is that there may have been, well, again, hydrothermal. There may have been local hydrothermal systems that mobilized the zinc, that caused the zinc to be deposited in the rim of the crater, and quite likely it was the heat that did it was actually associated with the impact event itself. When an impactor comes in, it's got an enormous amount of kinetic energy, blows a great big hole in the ground, but it deposits a lot of that kinetic energy as thermal energy. It heats the rocks up. And you can do the math, and what you find is that an impactor that would make a crater 20 to 25 kilometers in diameter can set up hydrothermal systems that can be active for thousands of years and can mobilize zinc carbon minerals. Now, it turns out that the Endeavour crater is remarkably similar in size to a very well-studied impact on Earth. Here's Endeavour. Here's the Reese impact crater in Germany, in southern Germany, at the same scale. So these are both really the same size. Here is a cross-section through the rim deposits of the Reese impact crater. And here, right on the rim, there are 2 different units. There's this thing called the Brunta breccia, which is a lithic breccia that looks just like Tisdale, just like Kid Creek. And on top of that, this is exactly what we see on the rim of Endeavour crater. So we're actually seeing stratigraphy on the rim that's a great match to what we see in craters on Earth. Okay, I got 5 minutes left. I'm going to go real quickly through this. One of the really fun things that we found as we were exploring along the rim of Shoemaker Ridge was a rock we call Homestead. Crazy looking thing. It looks like somebody with a jar of white paint and a paintbrush went out and painted white stripes on them. They're all over the place. When you look at them up close, it's this marvelous thing. And it's about as
wide as your thumb and about as long as your forearm. And there are a whole bunch of these. Here it is, looking at it up close with our microscopic imager. It forms a slightly raised ridge. When we measure the elemental chemistry of this thing, extraordinarily high in calcium, extraordinarily high in sulfur. If you take typical Mars composition and you follow that, it'll take you to pure calcium sulfate. So these are very high purity veins of some kind of calcium sulfate. We believe that it is gypsum. We have the ability to look at hydration of minerals with some of our PanCam color filters, and we compute something called a hydration index. When we do that for this vein, it just lights up. Okay, it has to do with the spectral parameters. If you crunch it with the wheels, like we did with innocent bystander, it lights up even more. And when you compare in detail the spectrum of this stuff, which is shown here, is the spectrum of different hydrated calcium sulfate minerals, gypsum is the best thing. So we think that these are gypsum veins. Gypsum veins are common. They're found on Earth where water percolates through fractures, rich in dissolved calcium sulfate, it precipitates it out. And so what we think happened here was that there was water that was oozing out of the shoemaker formation breccias. It dissolves away sulfates, and then the sulfates precipitate out in fractures that are immediately adjacent to Shoemaker Ridge. Why gypsum? Why the calcium sulfate? Where it turns out of those three sulfates, iron, magnesium, calcium, okay, that gypsum, the calcium sulfate, is by far the least soluble of the three, so it's the one that's going to be saturated first. It'll be the first to precipitate out. The others are still unsaturated, so you precipitate gypsum closest to the source. This is the road ahead. Opportunity's doing great. Today is day 3,133 in the mission. The rover's right there. We're about to head south. And Opportunity is about to do its first mountaineering, climbing eventually this point here that we named Cape Tribulation on the ridge that constitutes the rim of the Endeavour crater. And we're just going to keep going until the wheels fall off. I would be doing you and my team a great disservice if I gave you any kind of impression that somehow what I just talked about was my work. Okay, I am privileged to be the principal investigator of an extraordinary team of scientists. Here are their names. Here are their smiling faces. It's a magnificent team of scientists. I'm very proud to be part of that team. And finally, I also want to give an enormous amount of credit to the engineers who built these magnificent machines. I wrote a book about the project called Rover and Mars, and in an appendix to that book, I made an attempt to list the names of all the people who worked on this project, scientists and engineers alike. There are more than 4,000 names on that list. This is some of us at the Cape Canaveral. This is on the night that we sent the Opportunity spacecraft out to the launch pad. For every one of us who has had the remarkable experience of being part of this mission, it has been, in the literal sense of the word, the eventual lifetime. I want to thank you very much for inviting me. We have 8 seconds for questions. Oh, where the water came from? I wouldn't say it's completely unknown. I mean, there's plenty of evidence for there being groundwater levels. There's plenty of evidence today for there being ice beneath the surface, where water grows and it falls from essentially ice-rich rainfall, particularly at high latitude. So the question
not where did the water come from, because there clearly has been plenty of subsurface water on Mars. The question is what mobilized it, what made it move, what made it flow, okay? And when you look at, I mean, the story that you get in terms of the physics of what early Mars was like, it was a hot, steamy, violent place. There were volcanic explosions going on. There were volcanic eruptions going on. There was a lot of heat coming in from outside the planet, and then you had lots of impacts, and those bring heat as well. So my inference from looking both at the Columbia Hills and looking at the River Endeavor Crater, and looking at all this evidence for hydrothermal activity, the zinc, the silica, the alterations to make the gravitite and so forth, all of that points towards water activity at pretty low water to rock ratios, but heating that water up and causing it to move. It gets buoyant. Sometimes it turns to steam. It gets fumarole and so forth. So as long as you got the water present, you got a source of heat, you can kind of make this go. Yeah.
Long before the launch, I asked you how long it would take a geogeologist to do the same science that the rover does today, and you said 45 seconds. Which led to the Squire's number of 640, being the ratio between a human scientist and a rover.
I've never actually heard that.
For years, would you like to revise that?
No. Dave, what these rovers have done in 9 years on Mars, 6 years and 9 years, you and I could have done in a week or week and a half. Okay, where that comes from? The first time we ever fly a rover, we know about that one well. The first time we built a rover that was anything like this one, and took it out in the field, we took it out to the Mojave Desert, and of course, being a brand new rover, it broke down. And it wouldn't work. And so I had all these geologists with me who were bored because they had nothing to do while the engineers were fixing the rover. So I said, okay, look, let's go out and do some geology. And they had the boots and they had the rock cameras and the hand lenses. We went out and they started geologizing, doing geology. And I'd watch them and I'd time them as they look around. And as they walk over to an outcrop, our mobility system. As they reach down and break it open with a hammer, our rock abrasion tool. And as they look at it with their hand lenses, a microscopic imaging. And I would take how long it took them to do that and translate it into an equivalent number of Martian days. And yeah, what our rovers do in a day, these guys would typically do, and they were taking their sweet time about it too. They weren't rushing. And they would do it in 30 to 45 seconds. So yeah, it's a marvelous adventure that unfolds in excruciating slow motion. Yeah.
How is what it's doing now being coordinated with the latest rover?
I wouldn't say that it's being coordinated in any direct sense, but many, many, many of the lessons learned from 9 years of operating Opportunity and 6 years of operating Spirit have been folded into the way we operate the Curiosity. So our entire daily operations process for Curiosity. I mean, you go into one of these meetings and you have a bunch of scientists who have to decide what the rover's going to do that day. And if you've got 50 scientists, you're going to have at least 50 opinions of what the rover should do that day. And you have to reach a consensus, and over a period of literally hours, turn this into a validated set of commands that can be radiated to the spacecraft and actually executed in work. It's a complete contrast to the way most planetary missions work. I'm on the science team for the Cassini mission, to Saturn, wonderful mission. And when we're going to fly by one of the moons of Saturn, we can plan every observation months in advance. The geometry is known, all the constraints are known, and you have that sequence written, validated, locked down weeks before it's actually going to execute. Rover mission, you've got to plan what you're going to do today based on what you see in the images that just came down this morning. Okay? And so, in what you typically do in many weeks, you got to do in a matter of hours. And all of the processes that the Curiosity mission is using to do that very successfully so far, we've carried over from the lessons that we've learned in Spirit. So that's the coordination, if you will. We're operating one week based on what we know from the other side. Yes. there are both external and internal sources of heat, and as I said, there was a great deal of volcanic activity early in Martian history. For example, home plate, that plateau that I talked about, that's a volcanic plateau. That's not impact projected. And then, of course, we see lava everywhere. So there was an enormous amount of volcanic activity, so you had heat both from within and from within. Yeah?
So,
Yes. Excuse me? For the first 4 months of the Spirit and Opportunity mission, and for the first 3 months of the Curiosity mission, we operated on Martian time. The Martian day is 24 hours and 39 minutes long. You might think it's really nice to be able to sleep in an extra 39 minutes every day. It's not. Okay, so if our daily operations planning meeting starts at noon today, we're all living on Martian time, so that means tomorrow it starts at 12:39. And the next day it starts at 1:18. And 2.5 weeks later, you're going to work in the middle of the night. Thank God for grad students. And it cycles around. Now, when we first landed with Spirit and Opportunity, I got 2 rovers on opposite sides of the planet. I got to take my team, divide them in half. Everybody's living on Martian time, but in 2 different Martian time zones. And if you're working on Spirit and you want to switch to Opportunity, you get Martian jet behind. It was a rough way to live. We just went off Mars time with Curiosity a week or so ago, and everybody's very glad.
Yes, any evidence of organic compounds?
Carbon? We do not, with the Opportunity or Spirit rovers, have the capability to search for organic compounds. We don't have that capability on this vehicle. Curiosity carries a magnificent instrument called SAM. It was built just up the road here at Goddard Space Flight Center. It's a GCMS instrument that is capable of detecting organic parts per zillion level. And we just in the last few days made our first measurement of the composition of Martian soil. We're in the process of analyzing that right now for organics, but we have the capability with Curiosity to search for that, and to me that's actually the centerpiece of Curiosity mission. So stay tuned. Okay. Sure. Right there.
quick question. Is Curiosity permanently trapped in the crater that is landed?
Permanently trapped is the easiest way of putting it. We intentionally put it into a geologic wonderland, which is great. If we chose to, it's capable enough rover that we might actually be able to find a pathway out, but instead what we seek to do, it's a big crater, and centered within that crater is a 5-kilometer tall mountain of layered sedimentary rocks whose composition changes as you work your way up the stack. Plates at the bottom, sulfates at the top. We're going to find the whole thing. So we're very happy to be trapped.
I think we should do maybe just one more question. And then
One more, sure.
So do you see rovers playing a role elsewhere in the solar system?
Rovers elsewhere in the solar system, certainly on the moon. Certainly on the moon. There was a really interesting mission that was proposed recently to land on the backside, where none of the Apollo missions landed, where there's some unique, very different geology, big basin excavation through the mantle. We do a sample return mission, we buy sample return mission from there, it's great to have a rover that drives around. But you know, you kind of have to design the mobility system to be suitable for the environment you're going to. If you go into a place with a lot of gravity, you can drive around, and it's not too hot like Venus or too cold like the moons of Saturn. A rover's a good way to go. If you go to a low gravity object, like say a comet, it would be better to kind of hop around. So you want to design your mobility system to be specific to the environment you go to. Moon, and particularly Mars,